Let's continue with the talks. The first speaker this afternoon is Ioan Marcut from Nijmegen. He's going to talk us about Poisson cohomology of the dual of SL2.
Okay, thank you. And thanks to the organizers for inviting me to give a talk in this beautiful place. So I'll talk about, well, what the title says, the Poisson cohomology of a very particular Poisson manifold SL2R. And I've been here also last week during the school, and which was very well organized. And I'll try a bit to speak for everyone here, also for the students who maybe have seen some of the definitions just last week. So I hope everybody can follow this talk. So one thing that you've seen last week is that when you start with the Poisson manifold, M pi, where pi is a bivector field, to it you can associate, well, first of all, you have the algebra of multivector fields on that manifold. So these are sections of the exterior powers of the tangent bundle. This carries something which is called the Schouten-Nienhaus bracket, which satisfies a type of graded Jacobi identity. And the bivector field itself, in this is a differential on this algebra. And if you take the cohomology with respect to this differential, what you obtain is the Poisson cohomology of M pi, which I'll denote like this, so M pi. And moreover, because of the graded Jacobi identity, this operator acts as a derivation for the Schouten bracket. So also in cohomology, you have an induced bracket. And these Poisson cohomology groups are, in a way, the most basic invariants you can think about for a or maybe not. But are some of the most basic invariants that you can think about of a Poisson manifold. They were introduced already in the paper of Lichnerovich from the 70s, where basically Poisson manifolds were introduced, but besides defining them, it's somehow very, very hard to calculate these groups. So the only situations in which we have general techniques, well, the first one is when the Poisson manifold is symplectic. So for a symplectic Poisson structure, non-degenerate Poisson structure, the Ram complex is isomorphic to the Poisson complex, and then the Poisson cohomology is exactly the usual de Ram cohomology. So this would be one class of Poisson structures. Maybe I'll write it here. So there are relatively few results. So one would be, well, symplectic, but also other structures which are very close to be symplectic. Let me call them like mildly degenerate. So this would include, of course, well, symplectic, but also other versions of symplectic, like log symplectic, BK symplectic, scattering symplectic. If you don't know these words, don't worry too much. So these are all Poisson structures which are almost everywhere symplectic. They have some subset which is a hypersurface, usually, on which they degenerate. And these conditions tell you basically how bad they degenerate. Now, for these structures, Poisson cohomology has also been computed for many of these situations. And it relies also on the fact that you have a map from the de Ram complex to the Poisson complex. And then basically you can take the inverse by that map of all multivector fields, and you obtain some forms, which will be actually degenerate forms, in the sense that they will explode along this singular part. But using those techniques, this also can be somehow computed. So this is one extreme case. And the other one are what I would call compact type Poisson manifolds, or other people would call them like that. So compact type. And these are Poisson manifolds which have a nice symplectic groupoid integrating them. And then using the symplectic groupoid, you can still, well, nice meaning that the source fibers of the symplectic groupoid are compact, And you can view the Poisson complex in that situation as a subcomplex of foliated forms, invariant foliated forms on the groupoid. And there you can use either an averaging techniques or Hodge techniques. And this has also been understood for many situations. And maybe I will, well, one case here is the case of duals of compact Lie algebras. And about this, I'll say a little bit more very soon. And besides this, well, for regular Poisson manifolds, so for Poisson manifolds whose underlying foliation is a usual foliation, for those there is still a spectral sequence which converges to the Poisson cohomology, but to actually compute that, you have to compute foliated cohomology, which seems a bit more approachable, but it's still something which doesn't, well, it works in some situations, but there aren't that general techniques for that. Right. And what I'll talk about today will be the Poisson cohomology of SL2R. So let me just say a few things here. Right, so for every Lie algebra, you can associate to it so G, you have an associated linear Poisson structure. On the dual space. So the dual space is canonically a Poisson manifold. And, well, this gives you also one-to-one correspondence between linear Poisson structures on a vector space and Lie algebras. And in this case, at least the Poisson complex, you can write it in a very Lie theoretical way. So the space of multi-vector fields on G induced together with the Poisson differential as a complex, it is isomorphic with the space of, well, forms on G, so exterior powers of G star, tensor smooth functions on G star. So this really comes from viewing this as multi-vector fields, as constant multi-vector fields. And then on this side, what you obtain is the Eilenberg-Chevalier differential for the representation of G on C infinity of G star. So in this situation, the Poisson cohomology is the cohomology of this Lie algebra of G with values in an infinite dimensional representation. Right, so H will be usually the usual, the Eilenberg-Chevalier cohomology of the Lie algebra with values in G star. And for compact Lie algebras, this can be understood better. So if G is also a compact Lie algebra, then the Eilenberg-Chevalier cohomology of G with values in C infinity of G star, this is isomorphic. So this is something which holds for example, for finite dimensional representations and compact Lie algebras or semi-simple Lie algebras, but in the infinite dimensional case, it only holds for compact ones. So this is the usual cohomology of the Lie algebra tensor, the invariant part of the representation, where here G is a compact group, compact connected group integrating the Lie algebra. Right, so for such Lie algebras, you do understand this cohomology, but this already fails. So if I would just put here G semi-simple and non-compact, this already fails, this equality. So you always have a map from this cohomology in here, which is not surjective. So this was proven by Bursztyn, constructing some very specific classes, which he used to show that a big class of semi-simple non-compact Lie algebras are not, well, they don't satisfy the conclusion of Korn's theorem, to put it this way. And so this map is not surjective, and it's also not injective. at least for SL2R. Maybe that's something I'll get to a bit later. Okay, so now my plan is to discuss what is going on for SL2R, but maybe I'll try to keep also the general discussion on this part of the board. So to tell you what these groups mean in general for in low dimensions. And the lowest dimension, so the Poisson complex looks like this. So smooth functions on them, vector fields, bivector fields, 3 vector fields, and so on d pi. And now if you look at age 0 of m pi, well, so the map here is basically you take a function and look at its Hamiltonian vector field. So the H0 will be just the kernel of this map, and these are called Casimir functions. So these are Casimir functions. I will denote them by Casimirs of pi. And geometrically, these are functions which are constant, smooth functions on M, which are constant along the leaves. So smooth on M, which are constant along symplectic leaves. And or also you can think about them as being the center of the Poisson algebra of C infinity of M with the usual Poisson bracket. So now I'll discuss, well, SL2R a bit and tell you what happens in this case. So for SL2R, I will just identify it with R3 with the usual coordinates, and then the Poisson structure pi becomes x dy dz plus y dz dx minus z dx dy. And you have one of these Casimir functions, a basic Casimir function, which I'll denote by f is x squared plus y squared minus z squared. And a symplectic foliation of SL2R are basically come from the level sets of this function. So this is a Casimir of pi. Now if you want to, so what happens? If you look at this picture, so these are the level sets. You have symplectic leaves for positive values of f. You have this cylinder, so one-sheeted hyperboloids outside. For f equals 0, this level set, well, the way we think about symplectic leaves, we think about the upper part of the cone of f equals 0 as being one symplectic leaf, 0 itself being one symplectic leaf consisting of a single point, and the lower part of the cone as another symplectic leaf. So this is made out of 3. And then for f negative, you see that this splits, so the symplectic leaves are the two-sheeted hyperboloids, but they are distinct. They are not connected, right? So the upper part of such a one-sheeted hyperboloid and the lower part are two symplectic leaves. And Casimir functions being smooth functions which are constant along the leaves, you can also think about them, or in some situations, at least if the leaves are closed, you can think about them as being smooth functions on the leaf space. So when you start identifying the leaves and thinking about them as points. And this works quite well in this example. So maybe I'll explain this a little bit. So if you let's say, think about that you remove here 0, and you take, I'll call it y, is R3 minus the origin And then you identify all leaves. Well, you identify points which are on the leaves, on the same leaf. So I'll call this the regular leaf space. So what happens in this situation is that this regular leaf space is actually a manifold, a smooth manifold, but non-Hausdorff. And the way to visualize it is, well, you can think about starting with a line going like a vertical line, which cuts each leaf in one point and going this way. Right? So such a line will cut all the leaves besides the one in the lower cone. So I'll add another such line from z at minus infinity and do the same thing. And these two lines, well, they will cut all the regular leaves, but then when they get outside of the cone, here and here, you have to start identifying the points. Okay, so there are two lines, and then you have to identify some of the points. So basically, this y is in fact isomorphic or diffeomorphic because it is a smooth manifold to two copies of R glued along a half line. 0 infinity, right? So this is, if you teach a manifolds course, this is a nice example of a non-Hausdorff one-dimensional manifold. And our, let's say, the theorem 0, which is basically something that you prove just by checking things, is that the space of Casimir functions on for SL2R is isomorphic to the smooth functions on this regular leaf space Y. And how can we think about the smooth functions on this space? Well, they are basically pairs of functions, h minus and h plus. So both are h plus minus are smooth functions on R, but then which coincide on the half line 0 infinity. So h plus restricted to 0 infinity equals h minus restricted to 0 infinity. And, well, the map between the two, I think it's quite obvious now. So the smooth structure on the leaf space really comes from taking the quotient and such that the quotient map is a submersion. And then we just pull back functions. The only thing which is not completely obvious, but it's also very, very easy to check, is that they actually extend the smooth functions at 0. Okay? So maybe the theorem just says that they extend the smooth functions at 0. So this is the lowest dimensional case. And here, just because I'll use these functions a bit later on, let me also introduce some more notation. So this is, well, I'll use the notation Casimir. Then I'll also, okay, I have to check my notes. So I'll denote by C out. Locally, not globally. I'll write this more explicitly better. So the assignment, so h1, h minus h plus, goes to the function g, where g is given by h plus composed with f being this standard Casimir, x squared plus y squared minus z squared. This is for z positive, and h minus composed with f for z negative. And you have to check that this actually is glued together, right? So what happens here is that, well, locally every function is a function of f. It looks nicely here. You can extend it here, but there is no guarantee that in this lower part it will be the same function of f. Okay? So they can change. One remark here, I mean, the whole phenomenon that I'm describing is only interesting in the smooth category. If you start doing these things for analytic functions or polynomials, things are super easy. the only complicated thing comes from the fact that we're dealing with smooth functions, and then they are very, very flexible. So this C out, well, I put here an out because I'm looking only at functions which are supported outside of the cone, right? So this will be, I'll call them eta, which is a Casimir function for SL2R, such that the eta restricted to f negative equals 0, right? So they are supported only outside. And I'll take also a bigger space, which I'll call C flat, which are chi, also Casimirs of SL2 star, such that chi is a flat function at 0. So the infinity jet, so all the partial derivatives at the point 0 of chi are 0. Okay? So this, so C out is a subset of C flat, and this I'll use a bit later. In this description here, so what happens? C out are pairs of such functions which are equal, and they vanish on minus infinity 0. And this C flat are pairs of such functions such that both functions are flat at the origin. Okay, in this other perspective. So this I'll use a bit later. So now if you want to look at the next Poisson cohomology, so age 1, right? So you take the kernel of d pi, and the kernel of d pi are the Poisson vector fields. I'll just denote this like this. So Poisson vector fields of pi are simply vector fields on M which preserve pi, meaning that their Lie derivative is 0, which is, of course, equivalent to the fact that the flow of these vector fields is a Poisson isomorphism. And you can think about, so this is a subalgebra of the space of all vector fields. And you can think about it as being the Lie algebra of the group of Poisson diffeomorphisms of pi, right? So maps phi from, so diffeomorphisms of M which preserve pi, right? And I'm putting this between quotes because this object here, well, it's an infinite dimensional group. It's not a manifold in general. We know it's closed in the C1 topology, but that's pretty much, I think, we know in general about it. But somehow, well, if you take a path in this group and take its derivative at 0, you'll obtain an element here. And if you take a smooth path of Poisson of Poisson vector fields, which are complete or locally complete, their flow will be always by Poisson isomorphism. So in this sense, it plays the role of the Lie algebra. So this will be the kernel of this map. And then you have to mod out by the image of this map. Well, the image of this map will be simply Hamiltonian vector fields. So vector fields of the form xh, so the Hamiltonian vector field of h, where h is any smooth function on M. And you can also think, well, you can also construct a group associated to it. So this will be the Lie algebra of the Hamiltonian group of pi, which are, well, you take Hamiltonian vector fields and take their flows. Or more precisely, you have to take time-dependent Hamiltonian vector fields and take their flows, the ones that are well-defined. And what you obtain, the diffeomorphisms that you obtain, you can show that those form a group. So these are generated by flows of Hamiltonian vector fields. Okay, so this is. And then the relation between these two is, well, the Hamiltonian Lie algebra is an ideal inside the algebra of Poisson vector fields, and similarly, and therefore, and then H1 of M pi is the quotient, right? So it's the Poisson vector fields of pi modulo this Hamiltonian vector fields of pi. And therefore, you can think about it as being the Lie algebra. So this plays role of as this is in a way the Lie algebra of the group Poisson of pi modulo Hamiltonian of pi. So this group Hamiltonian of pi is a normal subgroup, and you can take the quotient, and it somehow plays this role, of course. To which extent this is actually a Lie group, that's very hard to understand in general. Right. So now I'll go back to our example here. So in this case, we build two vector fields. So for SL2R, we build two vector fields. Or let me write it, two Poisson vector fields. On R3 minus the cone. And the first one, let me call it T. So this vector field is built as follows. So T is given by, well, outside of the cone you have, or outside of the z-axis, you have the one from theta, which generates the differential of the angular variable, right? And this T will be simply pi sharp of this theta. Well, let me call it d theta. So this holds on the outside. So on F positive, and on F negative, I'll just put it as 0. Okay, so it will be a vector field. It's very, very unsmooth. Outside, well, it is only defined outside of the cone. Outside of the cone, it's smooth, but then here, here it becomes 0. And so this is one vector field, and I called it T because it will be tangent to the leaves. So it will be something which, on these outer leaves, it points upwards. Something like that, right? So if you think a little bit about, well, these leaves outside, they are all cylinders. They are symplectic leaves, so their Poisson cohomology is the same as their Dirac cohomology, and the Dirac cohomology of these cylinders is simply generated by this d theta. Okay, so this will play the role of, this will take care of the cohomology outside. And then inside, not inside, well, and then the second vector field will be normal to the foliation, and therefore I'll call it N, but I'm not really going to give you all the properties of N. It's just that basically this N is given by, is the partial derivative with F as a coordinate. So this vector field will be normal to the leaves, pointing outside. It's not defined on the cone. And well, if you apply to F to this basic Casimir, it gives you 1. Okay? So again, this is also not defined on the cone, but what happens is that, well, we give here some also very explicit formulas for N using charts upstairs and downstairs, which are adapted to SL2R. And I can't find the eraser. Yep. And then what happens is that if you multiply it with such functions, if you multiply any of them with flat functions, you obtain a smooth vector field, and with flat Casimir functions. So this will be theorem. Okay, maybe I shouldn't erase this right now. So theorem 1 will be that this H1 Poisson of SL2 star R pi is isomorphic to eta t plus chi n, where eta is one of these Casimirs which is supported on the outside, and chi is a flat Casimir. Right, so by this I mean that they have unique representatives of this form. Okay, every class has a unique representative of this form. Right. And what happens here is also a little bit special, because this, if you look at vector fields of this type only, so t times something, they form a subalgebra, right? So gt, which are vector fields of the form eta times t with eta in C out, this form a subalgebra. They are closed under the Lie bracket. And similarly also this Gn, these are closed under the Lie bracket, so eta n, where, chi n, where chi is a flat Casimir. Those are both closed under the Lie bracket. This is actually abelian, and this one normalizes this. So this depends on our specific choices that we get, but then you can also understand quite well this Lie algebra, H1, as a Lie algebra. It's really isomorphic to the sum of this, well, to the semi-direct product of these Lie algebras. Right, so what you obtain is, here is, you have the Hamiltonians of pi, and this is an ideal inside the Hamiltonians of pi semi-direct product with this GT. And this is an ideal then in Hamiltonian of pi semi-direct product with GT, semi-direct product with Gn, which are all the Poisson vector fields of pi. So this really forms a subalgebra, and so on. And the object that you obtain here are all the Poisson vector fields that are tangent to the symplectic leaves. Okay, so this is why this natural ideal shows up inside the space. And then you might start wondering what are the groups associated to this. And you can build some very natural groups. So for GT, you can build a group, I'll call it, write it here. So for GT, you can build a group capital GT. So this will be actually abelian, and it is, you basically exponentiate vector fields in GT, but then their flow will be very easy given. Like you basically move up along T with some distance eta. Basically, this is more or less what you have. So this is one group. And then for N, you can also build a nice group. I'll tell you first what is Gn. It's connected component. So of course, it will be something like generated by flows of elements in this Lie subalgebra. But on the other hand, well, this is the part of the Poisson cohomology which really acts on the leaves. So if you take their flows, they really do something transversal to the leaves, because n is transverse to the leaves. And you can actually view it as a subgroup of the diffeomorphism group of the regular leaf space. So this will be isomorphic to the group, let me write it like this, phi equals phi 1, phi 2. So this is, or maybe phi minus phi plus. This is a diffeomorphism of the regular leaf space of Y, such that so they preserve each component. So phi plus minus is a diffeomorphism of R, And then they coincide from 0 infinity on, so phi plus restricted to 0 infinity equals phi minus restricted to 0 infinity. And their infinite jet at 0 is that of the identity. Okay, so it's somehow a nice group. You can understand it by looking at the leaf space. It acts on the leaf space. And then the actual group Gn will be this Gn0, disjoint union with Gn0 times tau. So SL2R has an outer automorphism, which does something like this. So tau of x, y, z is minus x, or we put x, y, minus y, minus z. So this outer automorphism, it flips these two components. And on the leaf space, it also interchanges the two components somehow. And this is a group which you can associate to this Gn. Right, so. Say again? Which one? No. No, because they're not Hamiltonian. They do something on the cylinders. Around points. Not around the origin, but outside of the origin, they are. They are vector fields tangent to the leaves, foliated vector fields. Well, not the, yeah, the origin. I mean, all the craziness happens at the origin. And you can't really somehow say much, right?
If you remove the origin, those are the local Hamiltonian vector fields for the resulting regular processes.
Yeah.
Which extends smoothly at the
Yes. But every foliated, like for locally Hamiltonian or foliated is the same thing, no? For a regular Poisson manifold.
No, even by closed forms, which, by forms, differential vanish. Foliated symplectic.
Okay, I'm getting a bit confused right now, sorry. I can't think about these things on the spot. Right. So here I just wanted to say one thing. I mean, here you have the Hamiltonian group below. This will be a normal group in a semi-direct product with this GT, and will be also a normal subgroup in the group of Hamiltonian of pi semi-direct product with this GT semi-direct product with Gn. Right? It would be very interesting to know if these are all Poisson vector fields, Poisson automorphism of pi. So this is something we don't really know. At the Lie algebra level, this happens. This is something we can prove. So just to understand a bit also the classes here, how you can think about them. So if you start with any Poisson vector, Poisson diffeomorphism of M, of SL2R, the first thing what you can do is, well, look what it does on the leaf space, if it does something or not. So this will select this component over here, Gn. Okay? And because this Gn is really determined by what it does on the leaf space. So you can select that component and correct the diffeomorphism such that you get then a foliated one. Right? And then you can look at what it does on the leaves. And the leaves are these cylinders whose cohomology you understand quite well. So you can actually extract also the GT component. Right? So somehow if you want to prove this equality, you start with anything and you can reduce it to a Hamiltonian one. And then you start with something which you hope, which looks very much like a Hamiltonian one, but then you have to find a time-dependent function or something like this. Also at the infinitesimal level, it's exactly the same problem in a way, but it's simpler. It's a bit simpler. So we start with the Poisson vector field, and then we correct it by looking at this Gn component, that it's GT component, and we end up with something which is a foliated, as Rui would say, it's a locally Hamiltonian vector field, but we have to see if it's globally Hamiltonian. Right? And for that, we need to build a function. which would be the primitive along leaves. And for that, what we do, maybe I'll explain this quite shortly. So what we do is we need to and this is basically the most difficult part of the proof. So we end up with well, we are on SL2. On SL2R. And we have a bunch of foliated forms on the leaves, which we know that on each leaf this form is exact. And we want to build a smooth primitive to all of them. And for that, we use, like, if you were in R2 or in Rn, and how you can build primitives to a closed, in that case, is the same as exact form. You find a contraction to a point, and then you use some homotopy to that point, which gives you such primitives. Now, for us, what we do, we build something which we like to call the cohomological skeleton of the foliation. So this is really the z-axis and the z equals 0 plane. So what are the properties of this decomposition? So they intersect all the symplectic leaves in, well, let's look at the outer first. So they intersect them in circles. And the cylinders are homotopy equivalent to these circles. And the leaves, the one-sheeted hyperboloids, they intersect them in points. And these leaves are just plain, so they are homotopy equivalent to points, right? And well, what happens on the cone, that's a bit of a problem there. And maybe, to deal with that, we actually work with flat vector fields. So we reduce everything to flat vector fields by working with power series and so somehow you can reduce everything to flat vector fields and then flat forms. Right. And here, so this skeleton, let me just call it X, is this z equals 0 union with x equals y equals 0. You can construct a projection to it. I'll call it P from R3 to X, which does the following. So it's a foliated projection, and you start on a leaf, and you basically keep the same angle in polar coordinates and approach the point in X, depending on where you are. Right, so this will be one of these trajectories. Then in the interior leaves, you go down and you get to this point, and on the cone, you go directly to the origin. So you can contract everything to X. This resulting map P will be continuous, but not smooth. It will fail to be smooth exactly on the cone, but it will induce a homotopy equivalence for the forms that we're interested in. So somehow foliated forms which are flat at the origin. And this is how we build the, right. And to prove this, what we do, we take a vector field whose infinite flow is exactly this, P. So P will be the infinite flow of a very special vector field. So it will be a vector field which contracts everything to this X. And using this vector field, you can write homotopy operators, which give you primitives for these forms. And then you have to show that these are smooth. So that's somehow the hard part of the proof. Okay, I hope people understood a little bit what I tried to sketch here. I'll go on with telling you what is H2 now. So the second Poisson cohomology. So in general, for any Poisson manifold, H2 of M pi, the way we think about it, but this is already somehow more far-fetched than H1, is infinitesimal deformations of pi modulo trivial deformations. And the reason for that is that, well, if you start with pi and then start, and you have a smooth path of Poisson structures starting at that pi, if it's take its derivative, a consequence of the fact that all of these are Poisson structures implies that the derivatives of the starting speed is a closed element in the Poisson complex. And then if the family was given by an isotopy, so by moving by a time-dependent vector field, then the speed will be trivial. So this is basically the basis of this thinking, that these two things are equal. But then there are some more problems. I mean, you also have a bracket from H2 to H2, from H2 times H2 to H3, some sort of Kuranishi map, which gives you obstructions of having some classes, well, coming from deformations and so on. In our case, we have the following thing. So for SL2R, we have that H2 pi is given by the following elements. So it's eta T wedge N, where eta is one of these Casimirs, which is supported outside. So every class here can be uniquely represented like this. Again, so this T wedge N is a bivector field which is not smooth on the cone, but once you hit it with such a Casimir functions, it becomes smooth. Right? So all these infinitesimal deformations happen only outside of the cone. And what happens is that they are all Poisson structures. So this, for every eta, one of these Casimir functions which is supported outside, pi eta, which is pi plus eta T wedge N, is a Poisson vector field. Is a Poisson structure. Okay, and these were basically constructed already in the paper of Allen on the local structure of Poisson manifolds. So this is how he showed that there are Lie algebras they are Poisson structure which have a zero, and at the zero the isotropy Lie algebra is SL2, but they are not linearizable. So the way these look, these Poisson structures, maybe you should just, well, if you look in the z equals 0 plane, how they intersect the z equals 0 plane, then for the standard one, the leaves just intersected in concentric circles. And here somehow, well, it's a perturbation of this rotational vector field, what you obtain. So it could happen that you have a spiral around towards the origin, depending on how that function looks like. Or you could have here a closed circle and these spirals to this closed circle and so on. Or outside you could have a spiral in the other direction. Right? Is this a little bit clear what I mean by this? So this is how these Poisson structures look like. But what we don't know is if these are all Poisson structures around pi. So this would be somehow what the this infinitesimal calculation tells us. Well, it should tell us this, that are all Poisson structures near pi of this form. So this is something which we don't really know. And also another way to ask this question is, well, if you start with a Poisson structure, maybe it's even equivalent to this one. If you start with a Poisson structure which has a 0, and at that 0 the isotropy Lie algebra is SL2R, will it be isomorphic to one of these structures, right? But then, so this is one part. But then what happens is also that these are not all distinct, these Poisson structures. And this comes from the fact that the Lie bracket in cohomology from H1 times H2 to H2, this is non-trivial, the Lie bracket. This gives you the infinitesimal action of outer Poisson isomorphisms, or non-Hamiltonian Poisson isomorphisms on the space of deformations. So this will be the infinitesimal picture. And in our case, this group Gn acts on all these Poisson structures. Right, so Gn still acts, well, the GT part doesn't act on these Poisson structures, but Gn acts, or the action is trivial of GT on this pi eta, where eta is in C out. The action is non-trivial. Actually, only parts of it act, the one which changes something outside. And well, it would be nice to see if all identifications come from this action. So do all. So these are just, well, basically, we don't really know if this is the case, but this seems to be the case, infinitesimally. You can even understand quite well what this space is, like the quotient modulo. It looks a bit like adjoint orbits of the group of diffeomorphisms of the real line, which are supported only on the positive semi-axis. So it's a huge space. And it's the adjoint orbits of that group. So something like this is this space here. Okay. And finally, I'll tell you also what H3 is, which is somehow not very interesting, or I don't really understand what it means geometrically. But these are formal power series in one variable, which I'll denote by f, like our standard Casimir, dx, dy, wedge, dz. Right, so here, what happened? Well, maybe the only interesting thing about this is what I said at the beginning, that the map from the algebra cohomology tensor invariant functions is not an injective map. So in this H3, you can see that for SL2R. But more than that, I don't really, I mean, we can calculate this, but I don't really understand if it means anything geometrically somehow compared to all the other parts. I'll stop here.